So I hope this one will work better than the previous one. At least it has a nice picture to start off with. So in the strategic plan, we talked about a number of initiatives to do things like significantly strengthen or develop our expertise in areas like spatial analysis and geostatistics and machine learning and so forth, become a recognized center of expertise for applying and integrating airborne LiDAR data, and to become a nationally and internationally recognized leader in developing and distributing 3D and 4D geologic maps. So the question is, how do you do that? And you need one thing is people, and you also need hardware and software and computational capabilities. So I'm going to talk really briefly about what we're calling the Digital Earth Analysis Lab, because it's sort of a catchy acronym, and talk about some of the things we can do with it. So we've actually started working on the lab. We have a room identified. We've started renovating that. We have computers on order. I'll talk a little bit about the specific hardware, but what I'm going to talk about in this presentation is mostly what we can do with things like LiDAR. So one of the things that attracted me to the job here is that Kentucky is incredibly rich in geodata and geo-knowledge. And as it's come up several times through the morning, one of the things we need to do is start integrating that and working with it. So we have the complete geologic map coverage. We have a lot of thematic map layers, and this is a screen from our internet map service. Things like lithology and karst potential and oil and gas information, landslide locations, fault structure contours. We have some soil survey, the Surgo database. We have a lot of borehole data, outcrop data. And the really great thing, because this is what I've done for a lot of my career, I've done a lot of digital terrain modeling, both with airborne LiDAR and deep sea high resolution multi-beam bathymetry, is that by the end of the year or early next year, we should have complete airborne LiDAR coverage of Kentucky. Just let me ask, how many of you out there, especially geologists, have worked with airborne LiDAR on a project? So that's actually pretty good. When I started working on this, there would be like maybe 2 people in the room when I started working this about 15 or 18 years ago. So it's becoming more and more easily available. More and more people are using it. And I think it's one of those things, because I'm just a little bit too young to have been in the plate tectonics revolution. By the time I got to college, it was pretty much settled. There was the oddball who still insisted that no, they weren't really moving. But that was pretty much settled. So I missed out on that revolution. But in the 30 or so years that I've been working as a professional geologist, if you would ask me what's the most revolutionary change, especially as it relates to geological mapping, and I would say that's airborne LiDAR, because it's nothing short of phenomenal when it's done right in terms of our ability to understand the surface of the Earth. So I'm going to give you some examples of that. So that's one of the great things. By the end of the year, we'll have complete LiDAR coverage. There are very few states that can say that. No other state really, no other state of size can say that they have this complete geological map coverage. So now it's the time to pull those together. Well, what is airborne LiDAR? It's basically laser scanning from an airplane. So the acronym stands for light detection ranging. The really short version is you take an airplane or a helicopter, you cut a hole in the bottom, you put in a laser scanner, you send out now hundreds of thousands of pulses per second. When I first started doing this, 25,000 or 25 kilohertz was a good pulse rate. Now you can get up to 500,000 pulses per second. So you send out a lot of laser pulses. You know the aircraft location through GPS. You know its attitude through an inertial reference system. And you know the pulse orientation because you're sending it out in the scanner. And you send it out, you wait for it to come back. You actually get multiple returns as it bounces off treetops and bushes and ultimately the ground and buildings and cars and whatever else is in the way. You do some math. We won't go into that. Then you calculate the position that the laser struck the ground based on its travel time and that other information you've collected. You then remove trees and buildings and other things that as geologists we aren't particularly interested in, although people like foresters can use the trees, people like emergency managers and infrastructure managers can use things like power grid information. So it's all valuable information. But for us as geologists, the results is lots of topographic data, like millions upon millions upon millions of pieces of information about the topography of whatever area you're working in. So what's so special about it? On the right is a conventional 10-meter DEM. And I remember when those first came out, we were pretty excited and said, wow, look at the quality of topography you can get on the computer. So the upper one is a hillshade map. The lower one is a contour map. This is actually an area on the Kitsap Peninsula near Seattle where I used to live and work. So a lot of these slides are from other areas. Some are from Kentucky, but some I've pulled out from different things I've worked on over the years. On the left is a 2-meter LiDAR DEM. So the difference to me is phenomenal in terms of the level of detail that you can see between those two. Now imagine you're doing geology and you have your choice of which one of these are you going to use to base your mapping and your decisions on. And it goes even farther than that, because if you're working in a really rough, steep, forested area, I can make an argument, and this first occurred to me when I was working on a project in the equatorial jungles of Papua New Guinea. You can almost certainly do better geology by doing it first in the office, going to the field with working hypotheses and applying a field verification than you could if you were wandering around through the jungle with an air photo in your hand trying to scribble stuff down. I think it's that revolutionary. It fundamentally changes the way we think about mapping. Here's another example. This is actually partly in Kentucky. It's the Ohio River, and this is the area west of Cincinnati. It's sort of near and dear to me because that's where I did my PhD dissertation about landslides in the 1980s. The left is a state-of-the-art, modern, digital orthophotograph. A color, it's tree-off conditions, which is why the trees are brown. But look at that and ask yourself what you see in terms of landform, and especially landslides. The right is the 2-meter LiDAR digital elevation model of publicly available from the state of Ohio, showing what that terrain looks like when you take the trees off. And again, it's an amazing difference. I think how much better you can do geology when you have the topography on the right versus, say, the aerial photograph on the left. We can go beyond that, though, go beyond just making hillshade maps and use it to understand and visualize landscapes. So this is actually 2 USGS 7.5-minute quadrangles out near Pikeville. And off the top of my head, I can't remember the name. Bethany actually found these for me, so she might, I don't know if you remember. It's somewhere near Pikeville. But the main point is, you look at that, and even though it's a really high-resolution image, it's a complicated topography. So what we can do, because each one of those points is a number, and we know something about it, we can start doing things like numerically calculating attributes like roughness, which is the upper right-hand corner, and say, well, some areas of this map are rougher than other areas. And what does that mean? What does it mean in terms of landslides and land use and bedrock and hydrology and anything else we might care about? The one on the lower left-hand corner shows the topographic position index. That gets what Bethany was talking about the valleyness of an area. We can quantitatively say, not just we live in a valley, we live on a ridgetop, we can tell you where along that continuum we reside. And the one on the left shows actually curvature. So we can start quantifying, is this valley as open as the next valley? And does that make a difference? And these are all things we can calculate when we have millions upon millions of points to represent the topography. Here's a really neat example. It was picked out and sent to me by Sarah Johnson at Northern Kentucky University. She had a long-standing interest in mapping landslides in Northern Kentucky, and we're working together on a project. She said she found an area where between 2 subsequent LiDAR coverages, there was a new landslide. So this is up along the Ohio River in the Cope Formation, and this is 2007. And basically, there's no landslide here. Here's a coverage in 2012, and the landslide's there. Nobody knew about this landslide before, and it's not a big or terribly consequential landslide because it's not threatening anybody. But that's the power of LiDAR, to be able to see changes that small, a few feet in topography, in an area that's very heavily forested. We can subtract those 2 DMs, then it becomes even more apparent. So the blue is areas where the topography has gone up, the red is where it's gone down, but still there's a lot of noise, and you can see that straight line. When you look at that and say, well, gee, is there anything we can do to clean that up? And it turns out you can look at the bias, because there are areas where you should, for all reasons, get 0, or you would expect to get 0. In a lot of this area, 0 change. So you can say, well, look at the statistics of non-zero values in areas where we think there should be 0 change, and even realize that they change across the map area, so they're not stationary, and apply things like Gaussian filtering and get rid of the noise, and lo and behold, there's a landslide. So, and this is something that took me like 15 minutes to do in my office once I had the data. So again, it speaks to the amazing utility of LiDAR data. Some of you may have heard of the Oso Landslide in Washington, the terrible tragedy that wiped out entire village. Again, this is before, so they had this image before the landslide, in case anybody says, well, we didn't know there were landslides in this area. Again, it was covered with trees, and you would drive up there and you look across and say, gee, what a verdant sylvan valley. It's so peaceful and calm, and big Douglas fir growing all over. So you probably wouldn't see that, but the LiDAR sees it, and it was there. This is what happened in, like 30 or 40 seconds. And we can use that for change detection. It's in a paper I'm going to be giving in June at a landslide conference. But we can also start saying, okay, again, we have this data. What can we do with it? We can start using techniques of characterization and classification and machine learning And we can say, to a first approximation, we'll look at that map and say there are two areas, landslides and not landslides. And we can use things like fuzzy logic and over very large areas, and again, in a matter of seconds or minutes, come up with provisional maps saying, okay, we think the red is probably more likely to be ancient landslide deposits than the green. Process-based hazard assessment. This is actually a project I worked on years ago in Northern California in the Franciscan terrain. Very complicated, very steep. They got like 1.5 meters or 2 meters of rain a year. The tectonic uplift rates there were 4 millimeters a year. Things were literally falling apart. And we were looking at different ways to assess the impact of clear-cut logging on water quality. So we were looking at DEM physics-based landslide models. So in here, you take a digital elevation model, preferably with LiDAR, you put in soil unit layers, and you specify things like the soil shear strength in terms of probability distributions. You put in forest cover. There's different trees of different ages will have different root strengths that contribute to stability. You take into account the errors and uncertainties with all of those. You calculate a slope map, and in the end, you can calculate a map showing the probability that there should be a landslide for those given conditions. And you can do neat things. Here's one where the dark forest covers old trees, strong trees that contribute to root strength. Young areas are young trees, in a lot of cases clear-cut areas, and you can see why this was an issue because the green is areas that have been clear-cut in this watershed, and the company wanted to cut more. So the question was, would this cause a problem? So we were able to use these models to say, okay, we'll take all the old dark green trees, make them into young trees with reduced root strength to simulate the effects of clear-cut logging, and then we could actually quantitatively calculate the increase in probability that there will be a landslide as a consequence of logging. So we take this incredibly high-resolution topography, we take the information we know about geology, about things like geotechnical properties, we bring those all together, and we can start coming up with really powerful solutions like this. This is in Nepal. This is actually not LiDAR, I have to confess. This was made by hand. It's the Lupron Landslide, which is in the Gorkha district of Nepal. I worked on it like 2008 or 2009 or so because there was a village built on top of it, and the landslide had started moving during periods of heavy rain. So we surveyed it. I worked with a Nepali graduate student, wrote a paper about it, and that was that until April 25th in 2015, which was the Gorkha earthquake, was magnitude 7.8. So Lupron was 7 kilometers from the epicenter. And the village was completely destroyed, which is a tragedy. There were about 2,500 people living there. Only about 34 were killed because it was a nice spring day and they were mostly outside. And their stone buildings didn't collapse on the people who were outside. But the amazing thing is when you looked at before and after satellite imagery, the landslide didn't move that much. It moved enough to create a few new cracks, but it didn't move a lot. So what we can do now is take these physics-based models of slope stability, and in this case, seismic slope stability, run them and say, what's the probability, given what we know about the earthquake, its intensity, its magnitude, its peak ground acceleration, what we know about the geometry, the slope, the soil shear strength parameters, bring those all together and back calculate what's the probability that we had about a meter of movement on that landslide, and that's the green area. So you can say we can sort of do a forensic back calculation and say, yeah, the models actually were pretty good. It was a tragedy that the village was destroyed, but these models are actually fairly robust if we want to use them for landslide hazard assessment in large areas. And we can apply the same kind of technology to Kentucky. Here's one that our hydrology group did, Junfeng Zhu with us. I don't know if you can see that in light blue. There are sinkholes outlined. So sinkholes have surface expressions. We have incredibly detailed digital representations of the surface. We can easily pick out sinkholes by a variety of algorithms, and he's even gone farther in using machine learning techniques, like the so-called random forest technique, to identify those and be able to generate control areas and test areas and validate the method. So we're starting to use some really cutting-edge methods in geohazard assessment that we wouldn't be able to do really if we didn't have the LiDAR. This is a really neat example. I borrowed it from Louisiana. This is New Orleans and Lake Pontchartrain on the right. So this is what it looks like. In normal conditions, if you note, the red and orange areas are all below sea level. They're protected by dikes. So what happens if you have a flood to sea level? And you can see the utility here. If you look in the upper corners, you can actually map out on a block-by-block basis. Say if you're doing emergency response, like where can you drive? Where do you need a boat to get to? Where's the area completely flooded? Where might the streets be flooded, but the houses might not be? And then you can look at, say, what like a 1 meter flood would look like as well. Applications to other fields. We just talked a little bit about health and the issue of valleyness. Drew Andrews has been working a lot in Camp Nelson looking at archaeology and has used LiDAR for that, and just gave a talk at the GSA Southeastern Sectional Meeting. This is going across river to Ohio. That's the Serpent Mound. in 3 dimensions, which is pretty neat. That's a widely used data set for LiDAR training and things. So tremendously powerful. The other thing we can do is digital outcrop modeling, and you can do that with ground-based LiDAR. You can also do it with digital photogrammetry. This is a model made by digital photogrammetry from 16 photos taken at random locations, just so they're a little bit overlapping, using an algorithm called structure for motion. So it contains 33 million points to about centimeter accuracy. And we have those in the computer. We can rotate, we can zoom. I'll show you, we can actually map features. This is probably, it's probably about 25 or so meters high and maybe 100 meters or so long. Here's another one, a little bit smaller. This is probably 5 meters high maybe. And you can see there's a rockfall slab and obviously a very fresh scar. So we're using some virtual reality geological modeling software developed at the University of Manchester. So we can take that point cloud. That one, by the way, was only like 8 million points. So it was a tiny kind of thing. But we can go in and in real time map joint planes and instantly calculate the orientation of the bedding and the joints and use those for things like stability analyses. So we have that technology today. We have the data today, and we just need to capitalize on it. This is a similar exercise. This was an outcrop along I-90, going through Snoqualmie Pass in Washington. Very similar technology, creating a 3D model of the slope, and then saying we're going to color the different joint sets by different colors. So basically, you all remember 3-point problems from structural geology? The nice thing is you can go to these models. You can do like 5 million 3-point problems. Or you can have the computer do it. It's actually easier to have the computer do it than for you to do it. Because the computer doesn't use like tracing paper. You don't get eraser smudges and things, and you just give it a matrix equation and it does it. But then you can color the whole outcrop by the orientation of the fractures. And you can identify fracture sets maybe you didn't know were there, or the continuity of fracture sets. Maybe you see 1 or 2 fractures, and this instantly gives you a way to visualize the continuity of the fracture sets across the entire outcrop. And then the last slide is just we'll talk a little bit about the specifics of the digital analysis lab. So I said we have a room, we have computers on order, we're going to have a couple of dedicated mini tower workstations and 34-inch curved monitors. We're going to have an 80-inch touch screen for group collaborative work, ergonomic tables and chairs. One of the things that's really going to help is we've just recently gotten a high-speed internet connection to the Mining and Mineral Resources building. It runs at about 40 gigabytes a second, from what they tell me. I mentioned earlier this morning, we've been talking about some phenomenal potential cloud solutions with groups like Google and bringing their artificial intelligence technology to bear on problems in Kentucky. So that's what we'll be doing in this lab as well. And then we'll be fully stocked with all kinds of LiDAR point cloud and terrain modeling and remote sensing and photogrammetry software. And we're going to reach out to other groups at UK, the health initiatives we've talked about, the mapping initiatives, archaeologists, civil engineers. We think there's a broad base of people who can really make use of this kind of expertise that we'll have as a resource at UK. So that's the last of my slides. If somebody has a really quick question, I'll try to answer it. If not, I'll be here all day. So yeah, go ahead, Jim.
Well, in the last 10 years, the big problem with LiDAR was just the expense of having it flown. So you mentioned that by the end of the year, we hope to have the entire state covered. Where is that data coming from?
It's coming from the state. It's a statewide program. Right now, it's with the GIS group in Frankfurt, and Doug can give you the details about that. We're going to get copies of that and serve it. But yeah, traditionally, it has been expensive. I worked on that project I mentioned, Papua New Guinea, where they actually had to fly everything to this remote island, and that was obscenely expensive. But it was also the reason we're there. It's the world's 2nd largest gold deposit, or gold that's currently being mined. So to them, it was worth it. When you look at the value of it to a state or even a county, you can show over and over that the benefit to cost ratio is tremendous. And if you compare it to, say, sending surveyors out, and everybody at some point has to update their topography. So it's now the most economical way if you need to do that. So yeah, if you say, I want to survey this 1 acre out in the middle of nowhere, a lot of the expense is mob charges and flight charges. So yeah, it still can be expensive, but if you think intelligently, if you have like statewide or regional consortia, one, it's not nearly as expensive as it used to be. There's a lot of competition in the market. Technology's improved considerably. So it's much more attainable and more, in fact, the USGS is embarking on a national modernization of its entire national elevation program that's going to be based on LiDAR, except in Alaska, where it's being based on radar for technical reasons. So, I mean, the USGS is undertaking to map the entire country with LiDAR, so it'll be available, yeah.
Because it's coming from different sources, do you have is there going to be a problem on resolution from, you know, like Louisville does theirs and Lexington pays to have theirs done, but the resolution between 1 through time and 2 at the same time, different techniques that cost less, so somebody says, oh, we only need that type of resolution.
Yeah, I've actually encountered that on a number of projects over the years. So the short answer is yes, because you can actually get the individual pulses. You can do a lot with that. And when I'm teaching short courses, things I actually have some case history showing the ground strikes, and you can see where different surveys have been merged together. There was one in the Seattle area near a dam, and it involved a fault that was projected to be cutting across Puget Sound. And like 2 degrees off from that, and maybe 100 meters away, was a seam in the LiDAR data. Guess which one showed up? It was a stronger artifact. So we knew there was a fault there, but I spent an inordinate amount of time explaining that, yeah, but that isn't it. This is the fault. So the good thing, in a similar project in Papua New Guinea, we were looking for fault crossings on a pipeline across the highlands of Papua New Guinea. We could plot the individual ground strikes and say, if we don't see a fault where we think there should be one, is it because it's not there, which is good, or because it's there and the data aren't resolute to depict it, which is bad. And then you can go out there and trench it. So the answer is yes, but if you deal with it intelligently, you can actually address those problems and at least be cognizant of them when you're making decisions.